In a control room outside Geneva, a physicist stared at a number on her screen that should not have existed, a number suggesting that somewhere inside 27 kilometers of underground tunnel, a particle had just broken a rule physics has trusted completely for 50 years. Welcome to Pale Blue Drift. The rule in question sits at the very heart of what physicists call the Standard Model, the closest thing science has to a complete rulebook for how matter and energy actually behave at the smallest scales imaginable. A theory so thoroughly tested over the past half-century that finding even a single genuine crack in it would rank among the most significant scientific discoveries of this generation. For most of that half-century, the Large Hadron Collider, the largest and most powerful machine ever built by human beings, has searched for exactly that crack. And for most of that half-century, it has found nothing. The Standard Model surviving test after test after test, more thoroughly verified than almost any theory in the history of physics. That long, unbroken record may finally be showing its first real fracture, and the discovery came from somewhere physicists least expected to find it, buried inside the quiet, unglamorous decay of a particle most people have never heard of. To understand what actually happened, you first need to understand a particle called the meson, a short-lived, unstable particle produced constantly inside the Large Hadron Collider whenever protons traveling at nearly the speed of light slam into each other head-on. Mesons exist for only the tiniest fraction of a second before they decay, transforming into a shower of other, more stable particles, and it is precisely that decay, the exact pattern of particles it produces and the exact angles at which they fly outward from the collision, that carries an enormous amount of hidden information about the fundamental laws governing our universe. Physicists working on an experiment called LHCb, one of 4 major detectors positioned around the Large Hadron Collider's ring, have spent more than a decade focused specifically on one particular, extraordinarily rare kind of meson decay, a transformation so unlikely that the Standard Model predicts it should occur in only about 1 out of every million mesons produced. When it does happen, the meson transforms into a cluster of other particles, including a pair of muons, heavier cousins of the ordinary electron, following a quantum mechanical pathway so indirect and so convoluted that physicists gave it an unexpectedly playful nickname decades ago. Because the diagram physicists draw to represent this kind of decay, full of looping internal lines representing particles that exist only fleetingly as mathematical possibilities before vanishing again, happen to resemble, to a physicist doodling at a conference in the late 1970s, the unmistakable silhouette of a penguin. The name stuck, and researchers today still refer to this entire category of transformation as a penguin decay, a term now embedded seriously into the official scientific literature, despite its thoroughly unserious origin. Penguin decays matter enormously to physicists hunting for cracks in the Standard Model, for a very specific reason tied to how quantum mechanics actually works at this scale. Because the decay proceeds through this strange, looping, indirect pathway rather than a simple, direct transformation, it becomes exquisitely sensitive to the presence of particles that have never been directly observed, heavy, hypothetical particles that current colliders may not be powerful enough to create outright, but which could still, in principle, exert a subtle, indirect influence on decays like this one, nudging the resulting angles and probabilities away from what the Standard Model alone would predict. It is a bit like trying to detect an enormous, invisible object sitting somewhere in a dark room, not by seeing it directly, but by noticing how it subtly changes the sound of your own voice echoing off the walls around you. For over a decade, LHCb researchers have been slowly, patiently gathering an enormous dataset of these penguin decays, sifting through the wreckage of proton collisions occurring roughly 40 million times every single second, hunting for exactly this kind of subtle deviation. Individual measurements over the years occasionally seem to hint at a small discrepancy from the standard model's predictions, but each one, on its own, remained well within the range that could plausibly be explained by ordinary statistical fluctuation, the kind of random noise every physics experiment inevitably contains, especially when hunting for an effect this rare and this subtle. What changed recently was scale. Researchers analyzed a truly enormous dataset, encompassing roughly 650 billion individual meson decays collected over several years of the collider's operation. And when they measured the precise angles at which the resulting particles emerged from this specific penguin decay, the result diverged from the standard model's prediction by a margin large enough that the odds of it being pure random chance dropped to somewhere around 1 in 16,000. A level of statistical confidence physicists describe using a measurement called sigma, in this specific case landing just under 4 sigma. It is worth pausing here, because the language of statistical significance in physics can sound almost deceptively modest to anyone unfamiliar with just how demanding this particular field actually is. In most areas of science, a result this unlikely to occur by chance would already be treated as remarkably strong evidence, more than sufficient to publish, to build upon, to treat as settled. Physics, however, holds itself to a considerably higher standard specifically because of how frequently the field has been burned before by results that looked statistically compelling at first, only to quietly dissolve once additional data came in. The formally recognized threshold for claiming an actual discovery in particle physics sits at 5 sigma, corresponding to odds of roughly 1 in 1700,000, that a result this extreme could occur purely by random chance. The current finding, at just under 4 sigma, falls meaningfully short of that threshold, occupying a specific, carefully defined middle ground physicists describe as evidence, tantalizing enough to take extremely seriously, not yet strong enough to declare victory. What makes this particular result stand out from the countless other intriguing but ultimately unconfirmed anomalies that have come and gone throughout the history of particle physics is not simply its statistical strength on its own, but the way it fits into a much longer, more consistent pattern. Researchers involved in the analysis have been careful to point out that this finding does not stand alone. Several related measurements of similar meson decays, conducted over roughly the past decade by LHCb, had already shown smaller, related tensions with the standard model's predictions, individually inconclusive, but pointing in a broadly consistent direction. This newest, more statistically powerful measurement is being described by researchers directly involved in the analysis as a genuine confirmation of that decade-long pattern, rather than an isolated, standalone surprise appearing out of nowhere. Even more encouraging, from a scientific standpoint, is the fact that this result did not come from a single experiment working in isolation. A separate detector at the Large Hadron Collider, known as CMS, independently studied the very same category of decay and found a discrepancy pointing in the same direction, though with somewhat lower statistical precision than LHCb's larger, more specialized dataset. Two independent teams of scientists, using different detectors, different analysis methods, and largely different sets of collision data, arriving at a broadly consistent conclusion, is precisely the kind of cross-validation that makes a genuinely difficult to dismiss result considerably harder to dismiss. And yet, despite all of this, the researchers directly responsible for the finding remain notably, deliberately cautious in how they describe it, and it is worth understanding exactly why, because the reason connects directly to one particularly stubborn complication buried inside the underlying physics itself. The specific penguin decay being studied can, in principle, also be influenced by an entirely different, considerably more mundane process involving particles called charm quarks, a process that exists comfortably within the standard model itself, requiring no new physics whatsoever to explain. If these so-called charming penguin contributions turn out to be larger than current theoretical calculations suggest, they could potentially account for some, or even all, of the observed discrepancy, without requiring any genuinely new particles or forces at all. Untangling exactly how large this competing, entirely mundane contribution actually is remains one of the most difficult open theoretical problems connected to this entire line of research. And until it is resolved with considerably greater confidence, researchers are unwilling to claim they have found definitive evidence of anything beyond the standard model, however tantalizing the numbers currently look. This is precisely the kind of careful, patient uncertainty that defines the very best moments in experimental physics, a result significant enough to genuinely excite an entire international community of researchers, consistent enough across multiple independent measurements and separate detectors to demand serious attention, and yet still humble enough, still honest enough about its own remaining uncertainties, to stop well short of claiming victory before the evidence has fully earned it. That caution is not simply good scientific practice in the abstract. It is a lesson particle physics has learned, repeatedly, the hard way, and it is worth spending a few minutes walking through exactly why, because the history of this field is scattered with moments that looked, for a while, remarkably similar to what researchers are seeing today, only to quietly dissolve once more data arrived. In December of 2015, two separate detectors at the Large Hadron Collider, working independently, both reported an unexpected excess of paired photons at a specific combined energy, a signal that briefly reached a statistical significance approaching 4 sigma, tantalizingly close to the threshold required for an official discovery. The physics community reacted with genuine excitement, and in the following months, hundreds of theoretical papers were written attempting to explain what kind of new, undiscovered particle might be responsible for the signal. When researchers gathered additional data throughout the following year, the excess simply vanished, revealed to have been an unusually persistent statistical fluctuation rather than any genuine new physics, a humbling reminder for an entire generation of physicists who had allowed themselves to hope, just a little too early, that a genuine discovery had finally arrived. That was far from the only time this has happened. Decades earlier, in the mid-1990s, an experiment called LEP, a predecessor to the Large Hadron Collider built along the very same underground tunnel, recorded an excess of events reaching nearly 4 sigma in significance, a signal that appeared briefly to resemble what researchers were searching for as evidence of the Higgs boson years before it was actually confirmed. That signal, too, faded away as additional data accumulated, turning out to be nothing more than statistical noise. In the late 1990s, a separate experiment at Fermilab's Tevatron Collider recorded an anomaly involving unusual particle jets, reaching an even higher statistical significance of 6 sigma, comfortably above the formal discovery threshold. And that signal, too, simply never reappeared in any subsequent data, becoming, in hindsight, one of the more stunning false alarms in the field's history. Even a claimed discovery of an entirely new category of particle called a pentaquark, reported by a separate laboratory in the mid-2000s with a similarly striking statistical significance, ultimately failed to hold up under further scrutiny from independent experiments. Physicists studying today's meson penguin decay anomaly are acutely, explicitly aware of this history, and it shapes every single public statement they make about the current result. The pattern connecting all of these earlier false alarms is instructive. Each one, in isolation, looked statistically compelling at the moment it was first announced. What ultimately separated the false alarms from genuine discoveries, in every case, was simply more data, gathered patiently over months or years, either reinforcing the original signal or gradually revealing it to have been an unlucky statistical fluctuation all along. This is precisely why researchers working on the current penguin decay result keep repeating the same careful qualifications, that the finding is significant, that it is consistent with a longer pattern building over roughly a decade, and that it still requires considerably more data before anyone can respectably claim it represents a genuine crack in the standard model, rather than simply the latest entry on a list of tantalizing anomalies that eventually faded away. Encouragingly, unlike several of the historical false alarms just described, researchers studying this particular anomaly are not required to simply wait and hope for an entirely new dataset to eventually materialize from scratch. The LHCb experiment has already collected roughly 3 times as many meson decays as were included in the current published analysis. Additional data gathered continuously since the original dataset was assembled, sitting available right now, waiting to be processed through the same painstaking analytical pipeline that produced the original result. Researchers expect meaningful, updated results incorporating this larger dataset within the next year or two, a considerably shorter wait than the multi-year gaps that separated many of the historical false alarms from their eventual resolution. Looking further ahead, an even larger opportunity awaits in the following decade, when the Large Hadron Collider is scheduled to undergo a significant upgrade, dramatically increasing its collision rate, eventually producing a dataset roughly 15 times larger than the one currently informing this analysis. If the anomaly identified today survives that eventual, enormous influx of new data, still showing the same consistent deviation from the standard model's predictions, it would very likely cross the formal 5 sigma threshold required for an official discovery, and researchers throughout the field describe that specific possibility as representing the most significant revision to particle physics in the 50 years since the standard model itself was first assembled. It is worth spending a moment imagining what such a confirmation would actually mean if it eventually arrives. The specific theoretical explanations researchers are currently considering to account for this deviation include the possible existence of an entirely new category of fundamental particle, sometimes called a leptoquark, a hypothetical particle capable of directly connecting 2 categories of matter, quarks and leptons, that the standard model currently treats as entirely separate families obeying entirely separate rules. Another possible explanation involves a heavier, undiscovered cousin of a known particle called the Z boson, sometimes referred to informally as a Z prime, capable of subtly influencing this specific decay through exactly the kind of indirect quantum pathway the penguin diagram represents. Either possibility, if eventually confirmed, would represent the first genuinely new fundamental particle added to physics's official inventory since the Higgs boson was confirmed in 2012, and the first evidence of any kind pointing toward physics existing meaningfully beyond the standard model in the entire history of the Large Hadron Collider's operation. Whatever this ultimately turns out to be, an ordinary, if subtle, quirk of standard model physics finally explained through more precise theoretical calculation, or the first genuine crack in 50 years of remarkably successful theory, the answer is not yet decided, and the researchers who have spent over a decade patiently gathering the evidence are the first to say so, clearly, repeatedly, and without a trace of the overstated certainty that so often creeps into how discoveries like this one get discussed once they leave the laboratory and reach a wider audience. To really understand why physicists are simultaneously excited and deeply cautious about the current penguin decay anomaly, it helps to understand a closely related story from the very same corner of physics, one that unfolded over the better part of a decade, built slowly into one of the most talked about anomalies in the entire field, and then, almost overnight, quietly disappeared. It begins with a concept called lepton universality, one of the standard model's more elegant and more unusual underlying assumptions. Physics recognizes 3 distinct types of charged lepton the ordinary electron familiar from chemistry classes, and two heavier, unstable cousins called the muon and the tau, both essentially identical to the electron in every way except mass. Lepton universality states that, aside from those mass differences, all three particles should interact with the other fundamental forces of nature in exactly the same way, meaning that any process capable of producing an electron should, once you correct mathematically for the different masses involved, produce a muon or a tau with equal likelihood. It is not a law of nature anyone has ever derived from some deeper principle. It simply falls naturally out of the mathematical structure of the Standard Model itself, and testing whether it actually holds true has become one of the most sensitive available tools for hunting down any hint of new physics hiding just beyond our current understanding. Starting around 2014, LHCb researchers began measuring a specific quantity called R of k, essentially a direct ratio comparing how often a B meson decays into a kaon plus a pair of muons versus a kaon plus a pair of electrons. If lepton universality holds perfectly, as the Standard Model demands, this ratio should land almost exactly at 1. The earliest LHCb measurements, however, consistently came in below 1, suggesting muons were being produced somewhat less often than electrons in this specific decay. A genuinely strange result if true, since nothing in the Standard Model gives any reason to expect leptons to behave differently from one another in this particular way. That first measurement carried a statistical significance of only around 2.5 sigma, interesting, but nowhere near strong enough to draw any firm conclusion. Over the following years, however, the pattern seemed to strengthen. Additional, related measurements, examining slightly different B meson decays involving a particle called K star instead of an ordinary kaon, showed similar deficits. Angular measurements of exactly the kind we discussed a few minutes ago, tracking the precise directions particles fly outward from these decays, showed their own smaller tensions pointing in a broadly consistent direction. By the early 2020s, an entire cluster of related measurements, sometimes collectively called the B anomalies, had built into one of the most closely watched, most discussed potential signs of new physics anywhere in particle physics, drawing enormous theoretical attention, with hundreds of papers proposing specific new particles, frequently leptoquarks very similar to the ones being discussed in connection with today's anomaly, capable of explaining exactly this kind of muon versus electron asymmetry. Then, in December of 2022, LHCb released an updated measurement, using considerably improved techniques for identifying exactly which particles had actually been produced in each collision, techniques capable of catching a specific, subtle source of error that earlier analyses had not fully accounted for. Certain hadrons, more common and heavier particles produced constantly in these collisions, could occasionally be mistakenly identified as electrons by the detector, subtly and systematically undercounting the true number of electron pairs being produced, and therefore artificially deflating the measured ratio below its true value. Once this specific background contribution was properly accounted for, the anomaly that had been building for the better part of a decade simply vanished. The updated ratio landed squarely in agreement with the Standard Model's prediction, and the broader pattern of related B anomalies largely evaporated alongside it. The reaction throughout the particle physics community was, by most honest accounts, a mixture of professional relief and genuine, personal disappointment. An entire cohort of younger physicists had built substantial portions of their early careers around theoretical models specifically designed to explain the now vanished anomaly, and the sudden, quiet resolution left many of them needing to pivot their research in an entirely different direction. It became something of a wry, self-deprecating joke within the field for a while, physicists describing the update as receiving, once again, nothing more than a very reliable, very familiar pair of Standard Model socks, instead of the exciting new physics toy so many had spent years hopping for. This particular history matters enormously for understanding today's penguin decay anomaly, and not simply as another cautionary tale about false alarms. It matters because the two anomalies are physically connected, arising from closely related decay processes governed by many of the same underlying quantum mechanical pathways. When the lepton universality anomaly evaporated in 2022, it did not fully resolve every related tension in this broader category of B-meson physics. The specific angular measurement behind today's penguin decay result was a separate, distinct observable from the ratio that ultimately dissolved, one less susceptible to the specific electron misidentification problem that had undermined the earlier result, and researchers directly involved in both analyses have been careful to emphasize that today's finding rests on a meaningfully different experimental foundation, immune to the specific systematic error that ultimately explained away its now infamous cousin. That distinction matters, but it also explains precisely why researchers remain so deliberately, publicly cautious this time around. Having watched one closely related, similarly exciting anomaly build for the better part of a decade, only to dissolve almost overnight, once a subtle systematic error was finally identified and corrected, nobody currently working on the penguin decay result wants to repeat that same experience of premature excitement. However carefully today's measurement has already accounted for the specific technical pitfall that undid the earlier finding. There is one more thread from this broader family of B-meson anomalies still worth mentioning, because unlike the lepton universality measurements involving electrons and muons, it has not yet disappeared and remains an active, unresolved puzzle running in parallel with today's story. A separate ratio, comparing decays involving the heavier tau lepton against the lighter muon in a different category of B-meson transformation, has shown a persistent, moderate deviation from the standard model's prediction across measurements from multiple independent experiments over several years, a tension smaller in statistical significance than the now-vanished lepton universality anomaly ever reached, but notably more durable. Having survived several rounds of improved measurement without dissolving the way its cousin eventually did. Researchers studying this separate tau versus muon puzzle remain genuinely uncertain whether it represents a real hint of new physics or simply an unusually persistent, still unexplained systematic effect waiting for its own eventual resolution. And it continues to be studied alongside today's penguin decay anomaly as part of the same broader, ongoing effort to understand whether the standard model's elegant assumption of lepton universality truly holds without exception, or whether it quietly breaks down somewhere in the specific, rare corners of particle physics. Researchers have only recently gained the tools to examine this closely. There is a similar, if unrelated, cautionary story worth mentioning from an entirely different corner of particle physics, involving not B-mesons at all, but the humble muon itself, and the exact strength of its own tiny internal magnetism. For years, an experiment first conducted at Brookhaven National Laboratory, and later repeated with even greater precision at Fermilab, measured this property, known formally as the muon's anomalous magnetic moment, and found a small but persistent discrepancy from theoretical predictions. Another long-standing, closely watched hint that new, undiscovered particles might be subtly influencing the muon's behavior in ways the standard model alone could not explain. That anomaly, too, appeared to strengthen with additional data throughout the 2010s and into the 2020s, becoming, for a time, one of the most widely discussed potential cracks in the standard model anywhere in physics. Then, in 2023, an improved theoretical calculation, incorporating more sophisticated techniques for modeling the complicated quantum interactions involved, produced a revised prediction considerably closer to the experimentally measured value, suggesting that at least part of the original discrepancy may have reflected an incomplete theoretical calculation rather than genuine new physics, though the full resolution of that particular puzzle remains, itself, an actively contested and unfinished conversation within the theoretical community even today. Taken together, these three intertwined stories, the lepton universality anomaly that built for a decade and then vanished, the muon magnetism puzzle that has partially, though not entirely, resolved itself through improved theory, and the ongoing tau versus muon tension that has so far refused to either disappear or fully confirm itself, form the immediate scientific backdrop against which today's penguin decay result is being carefully, skeptically evaluated by the very same community of researchers who lived through watching each of those earlier stories unfold. It is worth spending a few minutes now going deeper into exactly what a leptoquark, the leading hypothetical particle researchers are currently considering as a possible explanation, would actually mean for our broader understanding of the universe, because the implications reach considerably further than simply explaining one unusual meson decay. The Standard Model, as currently constructed, treats quarks and leptons as two entirely separate families of fundamental particle, governed by distinct sets of interactions, with no direct force capable of transforming one directly into the other. This separation has always struck many theoretical physicists as slightly unsatisfying, an arbitrary-seeming divide in a theory that is otherwise remarkably elegant and unified in how it describes the other fundamental forces of nature. A leptoquark, if it genuinely exists, would represent an entirely new category of fundamental force, capable of directly connecting these two previously separate families, allowing a quark to transform directly into a lepton, or vice versa, under very specific, rare circumstances. Such a particle would not simply patch one specific anomaly in one specific meson decay. It would suggest an entirely new layer of physics operating at an energy scale beyond what the Large Hadron Collider is currently capable of directly producing, detectable, for now, only indirectly, through exactly the kind of subtle statistical fingerprint researchers are currently studying in decays like this one. Several theoretical frameworks proposing leptoquarks were originally developed decades ago for entirely separate reasons, attempting to explain other unrelated puzzles in particle physics. And part of what makes the current anomaly interesting to theorists is that some of these pre-existing leptoquark models, developed without any specific reference to meson decays at all, turn out to naturally predict a deviation of roughly the size and character currently being observed. A coincidence that, while far from proof, has genuinely intrigued a significant portion of the theoretical community. The alternative explanation, a heavier, undiscovered cousin of the Z boson, sometimes called a Z prime, carries its own distinct theoretical implications, generally emerging from models proposing an entirely new, additional fundamental force of nature beyond the four already recognized by the Standard Model, one that happens to interact preferentially with muons rather than treating all leptons identically. Distinguishing definitively between a leptoquark explanation and a Z-prime explanation, assuming today's anomaly does eventually prove to be genuine new physics, would itself require an entirely new round of dedicated experiments, each hypothetical particle predicting slightly different, additional signatures that researchers could specifically search for once armed with the enormous new dataset expected from the Large Hadron Collider's planned upgrade in the following decade. There is also a broader, more speculative connection some theorists have proposed between these hypothetical new particles and one of the most enduring unsolved mysteries in all of physics, the true identity of dark matter, the invisible substance that appears to make up roughly a quarter of everything in the universe, detectable so far only through its gravitational influence on galaxies and galaxy clusters, never directly observed in any laboratory. Certain theoretical frameworks proposing leptoquarks or additional Z-prime style forces happen to naturally include a stable, otherwise invisible particle as part of the same broader mathematical structure. A particle that could, in principle, serve as a viable dark matter candidate. This connection remains genuinely speculative, one of several possible threads theorists are exploring rather than anything approaching an established conclusion, but it illustrates why a result like today's penguin decay anomaly, however narrow and technical it might sound on its surface, has captured the attention of physicists working across many different specialties, each one wondering whether this particular thread, if it holds up, might eventually connect to some of the largest remaining open questions in the entire field. None of this excitement changes the fundamental, patient discipline currently guiding how the result gets discussed publicly. Researchers directly involved in the analysis continue emphasizing, in every interview and every published paper, that the result remains short of the formal discovery threshold, that a mundane, entirely standard model explanation involving those stubborn, charming penguin contributions has not yet been ruled out, and that the community's own recent, hard-earned history with the now-vanished lepton universality, anomaly, demands exactly this kind of restraint before anyone allows themselves to treat today's finding as a settled, genuine crack in 50 years of remarkably successful theory. There is something worth appreciating in this quiet, collaborative infrastructure that rarely gets much attention outside of specialist physics circles. Unlike a field where a single research group might work in relative isolation, protective of its own data until publication, particle physics at this scale has evolved a culture of near-constant internal scrutiny, where results are challenged, cross-checked, and stress-tested repeatedly within the same collaboration long before they are ever shown to the outside world. Working groups devoted specifically to identifying potential sources of systematic error, exactly the kind of error that eventually undid the lepton universality anomaly, exist as a permanent, ongoing feature of how these experiments operate, staffed by physicists whose entire professional role involves trying, as hard as they possibly can, to break their own colleagues' most exciting results before anyone else gets the chance to. That internal culture of rigorous self-doubt is, in its own way, one of the quieter triumphs of how modern physics actually operates, a discipline that has learned to build institutional skepticism directly into its own process, rather than relying purely on individual researchers to police their own excitement. It is precisely this culture that allowed today's penguin decay result to survive as long as it has without being quietly withdrawn or revised the way its lepton universality cousin eventually was. And it is precisely this same culture that will continue testing the result, relentlessly, patiently, against every new batch of data still to come. That same culture of relentless internal scrutiny is precisely what will determine what happens next, over the following months and years, as researchers continue working through the enormous, growing dataset sitting available to them right now. And it is worth walking through exactly what that process actually looks like in practice, because it rarely resembles the sudden, dramatic announcements that popular science coverage sometimes implies. The Large Hadron Collider is currently deep into what physicists call its third operational run, a multi-year period of continuous data collection that began after the most recent round of major upgrades to the accelerator and its detectors. Unlike the earlier dataset behind today's penguin decay result, drawn from collisions recorded between 2011 and 2018, this current run is producing collisions at higher energy and considerably higher rate than ever before, meaning that every additional month of operation adds substantially more raw material for researchers to eventually sift through in search of the same rare decay. LHCb specifically underwent a significant internal upgrade ahead of this current run, improving its ability to identify and reconstruct exactly the kind of decay behind today's anomaly with even greater precision than the original analysis achieved, meaning that when researchers eventually incorporate this newer data, They will not simply be adding more of the same kind of measurement, but a meaningfully more precise version of it as well. Processing a dataset of this scale into a finished, publication-ready result is a genuinely enormous undertaking, involving far more than simply running a single calculation once the raw collision data has been recorded. Researchers must first reconstruct, computationally, exactly which particles were actually produced in each individual collision, a task complicated by the sheer density of activity inside the detector, where multiple proton collisions frequently occur simultaneously within the same tiny fraction of a second, overlapping in ways that require sophisticated software simply to untangle before any physics analysis can even begin. From there, researchers must carefully filter out an enormous number of unrelated background processes capable of mimicking the specific decay they are searching for, understand and calibrate the detector's own imperfections and biases with extraordinary precision, and finally apply the same rigorous statistical framework used in the original analysis, adjusted and improved wherever possible, to the newly available data. This entire process typically takes well over a year from the moment data collection finishes to the moment a finished result is ready for publication, and it is not uncommon for a single analysis like this one to occupy the dedicated, sustained attention of dozens of researchers throughout that entire period, many of them graduate students and postdoctoral researchers for whom this specific measurement represents the central project of their early careers. There is a particular kind of patience required to work on a project like this, spending years focused on a single, narrow measurement, understanding fully that the eventual result might strengthen a genuinely historic discovery, or might simply confirm, once again, that the standard model remains exactly as complete and correct as it has been for the past half-century. Both outcomes represent, in their own way, a genuine scientific success, though only one of them would ever make international headlines. Beyond this next incremental update, expected sometime within the next year or two, an even larger transformation awaits the entire Large Hadron Collider program later this decade, when the accelerator is scheduled to undergo its most significant upgrade since it was first constructed, transitioning into what researchers call the high luminosity LHC. This upgrade involves replacing key sections of the accelerator's magnet system and substantially overhauling several of its detectors, including LHCb itself, with the specific goal of dramatically increasing the rate at which the collider produces particle collisions. Once complete, this upgraded machine is expected to eventually accumulate a total dataset roughly an order of magnitude larger than everything collected throughout the collider's entire operational history up to this point combined. For a measurement like today's penguin decay anomaly, an increase in available data of that magnitude carries enormous significance. Statistical uncertainty in a measurement like this shrinks, roughly speaking, in proportion to the square root of the total amount of data collected, meaning that even without any change whatsoever in the underlying physics, simply gathering 15 times more data would be expected on its own to meaningfully sharpen the current 4 sigma result, pushing it considerably closer to, or potentially beyond, the formal 5 sigma discovery threshold. Assuming the underlying anomaly is genuinely real and does not fade the way the lepton universality anomaly eventually did. If, on the other hand, today's 4 sigma deviation reflects some subtle, still unidentified systematic error, or an incomplete theoretical understanding of those persistent charming penguin contributions, the same enormous increase in data would be expected to gradually reveal that as well, the anomaly weakening rather than strengthening as researchers gain the statistical power to examine it with far greater precision than is currently possible. This is, in many ways, the honest, unglamorous heart of how genuine scientific discoveries actually get confirmed in a field like this one. There is no single dramatic experiment capable of definitively settling a question like this overnight. There is only the slow, patient accumulation of ever larger, ever more precise data sets, each one narrowing the range of possible explanations a little further, until eventually, after years or sometimes decades of this kind of careful, incremental progress, the evidence becomes overwhelming enough in one direction or another that the entire scientific community can finally agree on what has actually been found. It is worth taking a moment to sit with a broader historical parallel, because this specific pattern, a small, persistent anomaly slowly building in significance over years of careful measurement before eventually reshaping an entire field, is not new to physics. In the final decades of the 1800s, astronomers studying the orbit of the planet Mercury noticed a small, persistent discrepancy between its observed motion and what Newton's theory of gravity predicted, an extremely subtle drift in the precise orientation of its orbit that Newtonian physics simply could not account for. No matter how carefully astronomers refined their calculations or accounted for the gravitational influence of the other known planets, for decades, this remained a minor, frustrating puzzle, occasionally attributed to an undiscovered planet closer to the Sun that some astronomers even gave a name, before extensive searching eventually confirmed no such planet actually existed. It was not until Einstein's general theory of relativity emerged in 1915, offering an entirely new understanding of gravity itself, that Mercury's small, stubborn discrepancy finally found its explanation, not as a flaw in the measurement, but as genuine evidence that Newton's centuries-old theory, remarkably successful as it had been, was not the complete and final word on how gravity actually worked. That historical episode carries a specific lesson worth holding onto tonight, because it illustrates something important about how the very best, most consequential discoveries in physics often actually arrive. They rarely announce themselves as sudden, unmistakable revelations. They begin, instead, as small, persistent discrepancies, easy to dismiss, easy to attribute to measurement error or incomplete calculation, requiring years or decades of patient, careful verification before the scientific community can be genuinely confident that a real anomaly, rather than an overlooked mistake, is actually sitting at the heart of the puzzle. Mercury's orbit did not require Einstein to notice it. It required decades of careful, repeated astronomical measurement, verified independently by numerous observers, before the anomaly was considered solid and real enough to demand an entirely new theory capable of explaining it. Today's penguin decay anomaly sits, in its own way, at a broadly comparable stage of that same kind of long, patient process, though considerably earlier in its journey than Mercury's orbital puzzle was by the time Einstein finally arrived at his solution. It has been observed with real statistical significance, corroborated by a second, independent detector, and connects meaningfully to a broader pattern of related measurements accumulated over roughly a decade of careful study. What it still requires, before anyone can reasonably compare it to a discovery on the scale of general relativity, is exactly what Mercury's anomaly eventually received: additional years of increasingly precise measurement, conducted by multiple independent research groups, ruling out every plausible mundane explanation one careful step at a time, until the anomaly either dissolves entirely, the way the lepton universality puzzle eventually did, or becomes so thoroughly repeatedly confirmed that denying its reality would require ignoring an overwhelming, carefully assembled body of independent evidence. Whichever direction this particular story ultimately moves, the process itself, patient, collaborative, deeply skeptical of its own excitement, relentlessly checking and rechecking every possible alternative explanation before allowing itself to believe anything extraordinary, represents science functioning exactly as it is supposed to, slowly, carefully, and honestly, working its way toward whatever the truth actually turns out to be. There is a second historical parallel worth considering as well, one closer in time and closer in spirit to the specific kind of anomaly currently under investigation, because it involves a puzzle that took considerably longer to resolve than Mercury's orbit ever did, and offers a somewhat sobering, if ultimately encouraging, sense of just how patient this kind of investigation sometimes needs to be. For decades throughout the middle of the 20th century, physicists studying neutrinos produced by nuclear reactions inside the Sun found, again and again, that their detectors on Earth were consistently catching only about a third of the neutrinos that solar physics models predicted should be arriving. This discrepancy, known for years simply as the solar neutrino problem, persisted stubbornly across multiple independent experiments, using different detection techniques, built in different countries, over a period stretching more than 3 decades. For much of that time, the leading suspicion among many physicists was that the discrepancy reflected some subtle flaw, either in the detectors themselves, or in the theoretical models describing exactly how the Sun generates its own energy, rather than any genuinely new physics involving the neutrinos themselves. It was not until the very end of the 1990s and the opening years of the 2000s, when considerably more sophisticated detectors capable of distinguishing between different types of neutrino were finally constructed, that researchers definitively confirmed the true explanation. Neutrinos, it turned out, were not vanishing or being miscounted at all. They were changing identity during their journey from the Sun to the Earth, transforming from one type into another through a genuinely new quantum mechanical process called neutrino oscillation, a phenomenon the original, simpler version of the Standard Model had never anticipated, and one that required physicists to accept, for the first time, that neutrinos must possess a small but genuinely non-zero mass, a property the original theory had explicitly assumed to be exactly zero. That resolution, arriving after more than 30 years of patient, often frustrating investigation, ultimately earned a share of the Nobel Prize in Physics for the researchers who finally confirmed it, and it stands today as one of the clearest, most well-documented examples of exactly the kind of process currently unfolding around today's penguin decay anomaly, a persistent, statistically real discrepancy, initially suspected to reflect some overlooked mundane explanation. Patiently investigated across multiple independent experiments and multiple decades, eventually revealing itself to be a genuine, previously unknown feature of how the universe actually works, requiring a real, lasting revision to the Standard Model itself. It is worth being honest, in these final few minutes together, about exactly how long a process like today's might realistically take before reaching any comparably definitive resolution. The solar neutrino problem took more than 30 years. Mercury's orbital anomaly took several decades before Einstein's theory finally explained it, and even longer than that before the explanation was fully, independently confirmed through subsequent astronomical observation. Today's penguin decay anomaly, by comparison, has been building for a comparatively brief period, roughly a decade of accumulating related measurements, with the specific 4 sigma result discussed tonight representing only the most recent, most statistically powerful entry in that ongoing accumulation. Judged against these 2 considerably longer historical precedents, it would not be especially surprising if a fully confident resolution, in either direction, took another 5 or even 10 years of continued measurement before the scientific community reaches the kind of overwhelming consensus that both Mercury's orbit and the solar neutrino puzzle eventually achieved. That timescale might sound, to anyone hopping for a swift, dramatic answer, almost disappointingly slow, but it is worth reframing that patience as something closer to a genuine strength of the entire scientific process, rather than a frustrating limitation of it. Every one of the historical false alarms discussed earlier in this story, the vanishing diphoton excess, the disappearing LEP signal, the Tevatron's stunning but ultimately empty superjets, the lepton universality anomaly that built for a decade only to dissolve almost overnight once a subtle systematic error was finally identified, could have been prematurely declared genuine discoveries had the field been willing to move faster, act on incomplete evidence, or resist the kind of relentless, collaborative scrutiny that ultimately revealed each of them for what they actually were. The very same patience that makes today's story frustratingly slow to resolve is precisely what protects the field from repeating those same costly mistakes, again and again, every time a genuinely interesting but ultimately misleading statistical fluctuation happens to appear somewhere in an enormous, noisy dataset. If today's anomaly does eventually survive that entire patient process, emerging years from now as a fully confirmed 5 sigma discovery, rather than another entry on the field's long list of tantalizing false alarms, the consequences would extend considerably further than simply adding one new particle to an already crowded catalog of known physics. It would represent the first genuinely new piece of fundamental physics confirmed since the Higgs boson itself, more than a decade ago, and the very first direct evidence, in the entire history of the Large Hadron Collider's operation, that the standard model, for all its remarkable, decades-long success, is not the final, complete description of reality it has so often appeared to be. It would open an entirely new area of theoretical and experimental investigation, one that could, eventually, connect to some of the largest remaining mysteries in physics: the true nature of dark matter, the reason our universe contains far more matter than antimatter, or the deeper, still unexplained reason gravity behaves so differently from the other 3 fundamental forces the standard model already describes so successfully. None of that eventual outcome is guaranteed, and every researcher currently working on this specific analysis would be the first to say so clearly, repeatedly, without any of the overstated certainty that so often creeps into how discoveries like this one get discussed once they leave the laboratory. What is certain tonight is that the patient, careful, collaborative process required to eventually answer this question one way or another is already fully underway, continuing quietly in laboratories and universities scattered across the globe, exactly the way it has for the entire history of this remarkable, hard-won field: one careful measurement, one honest uncertainty, one painstakingly verified result at a time. What is certain tonight is that the patient, careful, collaborative process required to eventually answer this question one way or another is already fully underway, continuing quietly in laboratories and universities scattered across the globe, exactly the way it has for the entire history of this remarkable, hard-won field: one careful measurement, one honest uncertainty, one painstakingly verified result at a time. It is worth spending these final minutes together thinking about what it actually feels like to work inside a question this unresolved, because there is a particular kind of psychological discipline required of anyone who chooses to spend years of their professional life on a single measurement that might, in the end, simply confirm what was already known all along. Physicists who have spent their careers on searches like this one describe a very specific, familiar rhythm to the work: long stretches of painstaking, largely uneventful analysis, calibrating instruments, refining statistical methods, checking and rechecking sources of error, punctuated only rarely by a genuine moment of surprise, and even then, tempered immediately by the reflexive, well-trained instinct to distrust that surprise until it has survived every possible attempt to explain it away. That instinct to distrust your own excitement is not cynicism. It is, in a field that has been burned as often as particle physics has, something closer to professional wisdom, hard-won across generations of researchers who watched brilliant, promising anomalies dissolve, one after another, once enough additional scrutiny was finally applied. And yet, underneath that carefully cultivated skepticism, there remains, in nearly every physicist who has spoken publicly about today's result, an unmistakable undercurrent of genuine hope, a quiet, professional acknowledgement that this particular anomaly, unlike so many others that came before it, has now survived long enough and been corroborated independently enough that treating it as merely another passing statistical fluctuation feels, to many in the field, increasingly difficult to justify. That tension between hard-earned scientific caution and genuine, carefully restrained hope is perhaps the truest emotional description available of where this entire story currently stands. Nobody knows, tonight, whether the researchers currently working through the next round of LHCb data will eventually confirm this anomaly beyond any reasonable doubt, watch it quietly fade the way its lepton universality cousin once did, or find themselves, years from now, still caught in exactly the same frustrating, unresolved middle ground the tau versus muon puzzle has occupied for years already. LHCb is not the only experiment currently capable of contributing meaningfully to this particular question either, and it is worth knowing that an entirely separate detector, built and operated on the opposite side of the planet, is quietly working through its own related measurements at the same time. An experiment called Bell-II, based at a laboratory in Japan, studies particle collisions using a fundamentally different technique than the Large Hadron Collider, colliding electrons and their antimatter counterparts together at far lower energy, but with an experimental design specifically optimized for producing exactly the kind of meson decays central to tonight's story in extremely large, exceptionally clean quantities. Free from much of the background noise and overlapping collision debris that complicates analysis at a proton collider like the LHC. Researchers at Bell-II have been steadily accumulating their own independent dataset relevant to several of the anomalies discussed tonight, and their eventual, independent measurements will serve as another crucial cross-check, entirely separate from LHCb's own results, helping to confirm or challenge today's finding using a completely different experimental approach, built by an entirely different international collaboration, working from an entirely different set of underlying systematic uncertainties. This kind of redundancy, multiple independent experiments, using genuinely different techniques, converging on the same underlying physical question, represents one of the most powerful tools available to the entire field for distinguishing a genuine discovery from a subtle, instrument-specific artifact. It was precisely this kind of independent cross-checking, across multiple experiments and multiple detection techniques, that eventually resolved the decades-long solar neutrino puzzle we discussed earlier. And it is exactly this same kind of patient, multi-pronged verification that the field is currently counting on to eventually settle today's penguin decay anomaly as well, whichever direction the evidence ultimately points. There is something worth carrying with you from this story, beyond the specific technical details of penguin decays and sigma values and hypothetical leptoquarks, something closer to a broader appreciation for what genuine scientific progress actually looks like from the inside, rather than how it tends to appear once it reaches a headline. It rarely looks like a single, triumphant breakthrough arriving all at once. It looks like exactly what we have spent this evening walking through together. Small, persistent anomalies studied patiently for years, sometimes decades, cross-checked relentlessly by skeptical colleagues on multiple continents using entirely different instruments, tested against every plausible mundane explanation before anyone dares treat them as genuinely new, occasionally dissolving into nothing, and occasionally, after enough patient, careful work, revealing themselves to be exactly the kind of quiet crack in our understanding of the universe that eventually reshapes an entire field. For the younger researchers currently working on this analysis, many of them still early in their careers, having chosen this specific, narrow measurement as the focus of years of doctoral or postdoctoral work, the stakes carry a particular kind of personal weight beyond the purely scientific question at hand. Some among them will spend years of their working lives on a result that ultimately confirms nothing more than what the standard model already predicted, a genuinely valuable contribution to the field's overall understanding, but not the kind of career-defining discovery that arrives only rarely, for only a fortunate few, across an entire scientific generation. Others may find themselves, unexpectedly, present at exactly the moment a 50-year-old theory finally reveals its first genuine limitation. An experienced physicist who lived through the discovery of the Higgs boson in 2012 still describe, more than a decade later, as among the most significant of their entire professional lives. Nobody currently working on this measurement knows, yet, which of those two very different outcomes awaits them, and that uncertainty itself, carried quietly by hundreds of researchers scattered across the globe, is part of what makes this particular moment in physics worth paying attention to, regardless of how it eventually resolves. Somewhere beneath the French and Swiss countryside tonight, 27 kilometers of superconducting magnet ring sits largely dormant during this particular stretch of the collider's operational schedule, cooled to temperatures colder than deep space itself, waiting patiently for its next run of collisions to begin. And in offices and laboratories scattered across dozens of countries, physicists continue quietly working through mountains of already collected data, refining calculations, checking calibrations, slowly building toward whatever the next update to this story eventually turns out to be. None of it moves quickly. All of it requires exactly the kind of patient, careful persistence that built the entire field from its earliest days. One honestly uncertain result patiently followed by the next, until eventually, sometimes after a very long wait, the universe finally reveals a little more of how it actually works. Thank you for spending this long, quiet evening with us here at Pale Blue Drift, walking together through one of the more genuinely uncertain, genuinely fascinating open questions, currently sitting at the very edge of what physicists understand about the universe. If slow, patient mysteries like this one, still unresolved, still quietly unfolding somewhere in a laboratory far from wherever you happen to be resting tonight, are the kind of thing that helps your own mind settle into something calm and curious before sleep, there will be more evenings like this one waiting for you, more distant questions, more careful uncertainties, more long, unhurried stories built specifically for exactly this kind of stillness. For now, let the rest of tonight be simple. Somewhere far away, a machine larger than most towns continues its long, patient rest between collisions, and somewhere closer, your own thoughts can rest just as patiently, without needing to resolve anything at all before morning. Whatever the answer to tonight's quiet mystery eventually turns out to be, it will still be there, waiting, unhurried, long after you have already drifted off. Good night.